So here we've got two different functions being multiplied together, right? Yeah, 2z plus 5 cubed times 3z minus 1 to the fourth. So we've got a u and a v, which means we're going to have to use which rule?
Chain.
Well, we're going to have to use a chain rule, but before we need the chain rule, what rule are we going to use initially to even start to take this derivative? Yeah, product rule. So we're going to say y prime is equal to, and then we'll start with 2z plus 5 cubed. Then we need to multiply that by the derivative of 3z minus 1 to the fourth. So we can call this, we'll just call it, probably shouldn't use y equals 3z minus 1 to the fourth since y is already this whole function. Why don't we say a is equal to 3z, well, sorry, a is equal to u to the fourth with u equal to 3z minus 1. So that derivative should become 4u cubed. 4. Our u is 3z minus 1 cubed. And then the derivative of u should be 3. Everybody okay with that for the first part of the product rule? Okay, I'm going to assume that's a yes. And then plus 3z minus 1 to the fourth times the derivative of 2z plus 5 cubed. So we can say v is equal to u. Well, probably shouldn't use u again. We already used u. How about v cubed with v equal to 2z plus 5. So that ought to give us 3v squared. So 3 and then 2z plus 5 squared. And then the derivative of 2z plus 5, which is 2. Everybody okay with that being the derivative there?
I'm just unclear on how the 3 in the first term and then the 2 in the second term came about.
These ones? Here?
Yeah.
So when we did our derivative of the 3z minus 1 to the fourth part, we used the chain rule. So that should be 4u cubed for the derivative of a, right? But then we also have to multiply it by the derivative of u. That's the chain rule part. So we got to multiply by the derivative of 3z minus 1, which is just 3. And then same here, right? This is 3v squared times 2 times the derivative of the 2z plus 5.
Oh wait, for back to the first part, how is it 3z minus 1 to the power of 3 instead of 4? Like,
well, we're taking the derivative of u to the fourth, right? So that should be 4u cubed times the 3, the du dz, and we have 3v squared, the other one, times the derivative of the 2z plus 5 times 2.
wait, what is 4 the derivative of again? Like, man, I see 2z plus
4u cubed is the derivative of u to the fourth. So that's 4u cubed times 3. And then this is 3v squared times 2.
All right.
Everybody okay with that now or no?
Yes.
All right, cool. So now what happens if I ask you, when does this equal 0? A couple of the values are probably actually pretty obvious, right? Because they both this whole big term that's being added to this whole big term, they both have to equal 0 if we were going to have it equal 0. And so this would be, I mean, they wouldn't both have to, but they could both equal 0. And if z was negative 5/2, this term would be 0, which would make everything 0, right? And this term would be 0, which would make all of this 0. Same with if z was 1/3. but there might be other values. So we have to be able to factor this out cleanly to make it all one big multiplication. So what's in common in this first term and this second term?
3.
All right, they both got, let's see, they've even got, this one's got a 12, right? And this one's got a 6. So they both got at least a 6, right? So we could take the 3 out, but we could also take out a 2. So we could say 6, right? What else do they have in common? Do they both have some form of a 2z plus 5?
Yeah.
Yeah. So they have a 2z plus 5 to what power in common?
2.
Yeah, to the second. And do they have a 3z minus 1 in common?
To the third.
To the third.
Yeah.
All right, so now let's take a look at what's left in each one. So from this whole first big term, I took out 6, and there was a constant of 12, so that ought to leave me with a 2, right? I also took out 2z plus 5 squared, which ought to leave me with just a singular 2z plus 5 to the first power. And I took out a 3z minus 1 cubed, which doesn't leave me with anything, right? And then from the second term, so plus, I took out 3z minus 1 cubed, right? And I had a 3z minus 1 to the fourth, so that should just be 3z minus 1. And I took out a constant of 6, which I had a full constant of 6. And I took out 2z plus 5 squared. So I took out everything else. So that's our last term. Everybody okay with that?
Yep.
Cool. So we end up with y prime equals 6 times 2z plus 5 squared times 3z minus 1 cubed. And then this becomes 4z, right? Plus another 3z, which is 7z. And then plus 10 minus the 1, so plus 9. And so if I was asking you when this derivative was equal to 0, well, set to 2z plus 5, we'd end up with 3 values. 1 from here, z equals negative 5 halves. We'd end up with 1 from here, z equals a third. And we'd end up with 1 from here, z equals negative 9 sevenths, which we wouldn't have been able to just see from looking at the 2 terms being added together. We can only see that one once we factored it out. Everybody good with that?
And so if you ask for the derivative of this function, you want us to go all the way down to where we went?
If I just ask you for the derivative, this answer up here is perfectly fine with me. But if I ask you, when does this have a horizontal tangent line, and you have to set it equal to 0, I'm going to expect you to be able to factor it out and find all the values. So I'm never going to say, hey, if I'm just asking you for the derivative, you have to simplify. No, you don't have to simplify. But for the context of the problem, you need to know how to simplify it down and factor it out. Does that make sense? Yeah. Any questions there? Everybody okay with that or no? All right. Let's do another one. You guys want to try and work this one's derivative out on your own to start with?
Sure.
All right, so work out the derivative, and then if you want to try and simplify it all the way down, go for it, but we'll work through that together also. So this is 3x plus 1 to the 6th power times the square root of 2x minus 5. That's not a 6th root, but 3x plus 1 to the 6th power. All right, ready, go. So once again, it's the product rule, right? We got 3x plus 1 to the 6th times the square root of 2x minus 5. So our derivative, f prime, ought to be the first term, 3x plus 1 to the 6th times the derivative of root 2x minus 5. So the derivative of root 2x minus 5, that's root u. with u equal to 2x minus 5. Hold on 1 second. Sorry about that. So we end up with the derivative of root u, which is 1 over 2 times the square root of u, which is 2x minus 5, times the derivative of 2x minus 5, which is just 2. So I'll write over here, this is 1 over 2 root u, and this becomes 2. So that's where each of those came from.
And so there's many different ways of writing that, right?
Say that again?
There's many different ways of writing that, right?
You mean writing the 1 over 2 root u part, or?
Writing the 3x plus 1 to the 6th power. I wrote it as, like, I kept 1/2 as its own term, and then I put it as 1 over the square root of 2x minus 5.
Yeah, that should be fine. I can't exactly see what you're saying, but I think what you're saying sounds right.
Yeah.
Okay. And then we got plus, and now the root 2x minus 5 is just the term we're keeping. And we have 3x plus 1 to the 6th, so we'll call that v to the 6th, with v equal to 3x plus 1. And so when we do that, v to the 6th becomes 6v to the 5th, and 3x plus 1 becomes 3 when we take the derivatives. So we're going to have a 3 and a 6, which is going to give us an 18. And then we're going to have that 3x plus 1 to the 5th power. Good or no?
Good.
All right, I think it's probably a good idea for us to practice simplifying this. So the 2's should cancel out. And we're going to need a common denominator here. So if we want to get a common denominator, we're going to have to multiply this second part of it by root 2x minus 5 over root 2x minus 5. And now we can combine all of this together into one fraction. So we've got 3x plus 1 to the 6th plus 18 times 3x plus 1 to the 5th times root 2x minus 5 times root 2x minus 5 ought to just be 2x minus 5, and then a root 2x minus 5 in the denominator. Everybody good with the beginning part of the simplification?
Yeah.
Cool. All right. Then what? We need to do some factoring in the numerator. So what do they have in common?
3x plus 1 to the 5th.
Right, they both got this 3x plus 1, and the lowest power is to the 5th. So we'll take out a 3x plus 1 to the 5th, which will leave us with 3x plus 1 plus, this one's just a 3x plus 1, right? Plus 18 times 2x minus 5. Still all over root 2x minus 5. And now we should be able to simplify that to 3x plus 1 to the 5th. And then down here, we're going to have the 18 times the 2x is 36x plus the 3x is 39x. And then we're going to have minus 40 there, but plus 1, so minus 39. All over root 2x minus 5. Oops, 39, is that right? 39, that's not, why did I say 5 times 18 is 40? That's not even, I don't know, I must be tired. 5 times 18 should be 90, and then negative 90, and add the 1 to it gives us negative 89. Because of arithmetic, you know. Everybody good with that or no?
Good.
All right. Here we've got tangent cubed 4x. So this is definitely a composition of functions. So it's going to require the chain rule. How are we going to break this down into a composition? Y equals what in terms of u, with u equal to what?
Y equals tan cubed u.
All right, so let's look at that. We're not going to use this, but let's take a look at it. So y equals tangent cubed u with u equal to 4x. Now that's definitely reasonable, right? I mean, that's definitely a composition of two functions, and it definitely represents this function. No question about that. That's 100% correct. But the problem with the tangent cubed u is we need to be able to easily differentiate that, which we can differentiate that, but it requires using the chain rule. So if you end up with a y equals something in terms of u, and this piece here still requires the chain rule, you want to try and find a different thing for y to be. Going further out on this function. So like there's multiple compositions within tangent cubed of 4x. You chose to make u 4x, but we'd rather try to make u something else so that I can have a much simpler function as my y function. So anybody see one that will do that?
Y equals u cubed and u equals tangent 4x.
Yes, that's what we're going to end up using. Now, the derivative of y with respect to u is easy. The derivative of u with respect to x still requires the chain rule also, right? But that's okay. If it's in the u term that we need the chain rule, we'll just use the chain rule to differentiate it. So first off, we've got dy du equals 3u squared. And then du dx well, we're going to have to figure that out. Let's let u equal the tangent of v, with v equal to 4x. And then what would du dx be? It should be du dv times dv dx. It should be the chain rule on the u equals tangent 4x part. Everybody see that?
Yeah.
All right,
I
so
think-
what's,
Mr.
sorry,
Bachelor,
go ahead. Yeah.
I think when you on the right side, shouldn't it be v equals, or no, x equals tan v? Or wait,
No, that's u. So this is u, right? U is tangent 4x, so u is the tangent of something, with that
Oh, okay,
something
yeah.
being 4x.
yeah, okay.
All right, so what's the derivative of tangent v?
Secant squared v.
Secant squared v, and what's the derivative of 4x? Just 4, right? So what do we get as we put all this together? We got 12. We'll just call it f prime of x instead of dy dx. F prime of x is 12 u squared secant squared v. And all we have to do is replace the u's with our u's and our v's with the v. So this ends up being 12 tangent squared 4x secant squared 4x. Good or no? Any questions on that?
No.
All right. Let's see if we can find the slope of the line tangent to y equals sine to the 5th x at the point where x is pi over 3. You guys think you can do this one on your own using the chain rule? I think you can. All right, take like, I don't know, a minute and a half, 2 minutes to see if you can do what this is asking you to do. Find the slope of the tangent line to this curve. So find the derivative at pi over 3. Ready to go. What's the derivative of sine to the fifth? How do we do that? That should become y equals u to the fifth power with u equal to sine x. Everybody good with that?
Yep.
All right, so our dy du ought to be 5u to the fourth, and our du dx ought to be cosine x. So we should end up with y prime, or dy dx, is equal to 5 sine to the fourth x times cosine x. And if we want to figure out what that is, evaluate it at x equals pi over 3, well, just plug in pi over 3. We have 5 times the sine of pi over 3 to the fourth power times the cosine of pi over 3. And what's the sine of pi over 3?
Root 3 over 2.
Root 3 over 2 to the fourth, and the cosine of pi over 3 is a half. And so root 3 to the fourth power ought to be what? Ought to be 9. And root 3 times root 3 is 3. And you do that twice, that makes 9. So we got 5 times 9, which is 45. And in our denominator, we got 2 to the fourth times 2, or 2 to the fifth, which is 32. Good or no?
Good.
All right. Let's see if we can find all of the horizontal tangent lines for this function. Cosine 2x plus 2 cosine x. So let's work together to find the derivative on this one. We've got cosine 2x. That's cosine u, right? With u equal to 2x. If we want to find the derivative of cosine 2x, which ought to be negative sine u times 2, which would be negative 2 sine 2x. Everybody agree with that part, the first part of it?
Yeah.
All right. And then plus 2 cosine x just would be minus 2 sine x. That one doesn't require the chain rule, right?
Correct.
All right. So if we want to know when it has horizontal tangent lines, that means that we need to set the derivative equal to
Zero.
0, exactly. So we'll set this, which is our derivative, y prime, equal to 0. And how are we going to solve that?
Would we factor out a -2 first?
Sure, let's do that. So this will give us negative 2 times sine 2x plus sine x equals 0. And in fact, since this is just equaling 0, right, we can just divide by the negative 2 and just cancel it out. It's not going to be significant. How can I rewrite sine 2x?
2 sine x cosine x.
2 sine x cosine x plus our sine x is equal to 0. And now how do I solve that?
Factor out the sine.
Factor out the sine. Sine x times 2 cosine x plus 1 equals 0. Set each piece equal to 0. Sine x equals 0 and 2 cosine x plus 1 equals 0. And when on the interval from 0 to 2 pi does sine of x equal 0? Well, at x equals Come on, people. My 7-year-old laying on the couch with 101-degree fever just said 0. X equals 0. When else does the sign of x equals 0 between 0 and 2 pi?
Pi.
Pi, good. All right, and then 2 pi, but that's not actually included in our interval, so we won't include that one. And then this one gives us cosine x equals negative 1/2. When does cosine equal negative 1/2?
2 pi thirds.
2 pi over 3, good. And one other time between 0 and 2 pi.
4 pi thirds.
4 pi over 3, right? Second and third quadrant cosine should be negative and have a reference angle of pi over 3. So if we were to bring up Desmos and take a look at this, we should see that this is the case, that it has horizontal tangent lines at each of those values. So we had cosine 2x plus 2 cosine x, right? And if we look at 0, yep, that's a place where there would have been a horizontal tangent line. If we look at 2 pi over 3, there's one. Right here at pi, there's one. And at 4 pi over 3. Then we have another one up here at 2 pi, like we said, but 2 pi is not in the interval that we were given. Good or no?
Good.
All right. Last little thing we're going to do here with the chain rule from now, and we're going to move on to something else cool that you're going to need. So we want to show that the slope of every line tangent to y equals 1 over 1 minus 2x to the third power is positive, so that this always has positive sloped tangent lines. So how are we going to do that? We need to find a derivative first, right?
Right.
So this is 1 minus 2x to the negative third power, isn't it? Which ought to be y equals u to the negative 3, with u equal to 1 minus 2x. And what's the derivative of u to the negative 3?
Negative 3u to the negative 4.
Negative 3u to the negative 4. And the derivative of u with respect to x?
Negative 2.
Negative 2. Multiply those together, and you've got 6u to the negative 4, or 6 over u to the 4th, which gives you 6 over 1 minus 2x to the 4th. And what can you tell me about the numerator? 6 is positive, right? And what about the denominator?
It's raised to the 4th, so it'll always be positive.
Always going to be positive, unless it's 0, right? Unless 1 minus 2x equals 0. But if 1 minus 2x equals 0, the function's undefined, so there wouldn't be a tangent line anyway. So we don't have to worry about that. Right, so this is always a positive divided by a positive. And therefore, it's always going to be positive. Good or no?
Good.
Let's take a look, just for the heck of it, on Desmos. So 1 over 1 minus 2x to the third. And so you can see this is very, very slowly increasing until it starts increasing very rapidly. And if you were to pick any point on there and draw a tangent line, even though some of these are hardly increasing, it'd be going up ever so slightly. And then over here, they're definitely positive. And same thing on the other side, right? Very, very large positive numbers here, and then very quickly gets very small positive, but never has a tangent line whose slope is negative. Good or no?
Good.
Cool. All right. We are going to move into something new now. It's a new technique for taking derivatives, sort of a new technique for equations that are very different than what we've been dealing with. And we're going to call these things implicitly defined equations. And the differentiation that we're going to do is called implicit differentiation. So an implicitly defined equation is just an equation that does not necessarily pass the vertical line test. It's just not a function. It means that that equation is not explicitly written as a single function of x. It can't be written like all the other ones, like we did y equals sine x, right? That's y is something in terms of x, or y equals x cubed tangent to the 8th power of 7x minus 1, right? It's all written in terms of x. These are just regular old functions. Well, something like this, where I don't have it all written as y equals something in terms of x, is called an implicitly defined equation or an implicitly defined relation. That's just a relationship between x and y. And some of these that we'll deal with, there might be a relatively easy way for us to solve for y and do it normally. But for some of them, like for example, this one, x cubed plus y cubed minus 9xy equals 0, this one, there's no good way to just solve that for y. And even if you did solve it for y, you wouldn't end up with a single function, right? Because this does not pass the vertical line test, right? You're all familiar with the vertical line test?
Yes.
Yeah. Okay, cool. So, but we still might want to know, well, what's the slope of the tangent line at this point, or at this point, or at any point on here? And so we still need to be able to find a way to take the derivative. And so the way we do this is we take the derivative of both sides of the equation separately with respect to x. Now we're going to talk about how to do that in a second with a bunch of these terms that have y's in them, because taking the derivative of something with a bunch of y's in it with respect to x is not something we've done. True?
True.
Yeah. So when we do take that derivative, we're going to end up with a bunch of terms in it that are these dy dx terms that are just meaning the derivative of y with respect to x. And our goal will be to solve for dy dx, which will require us to factor out the dy dx and put them all on one side and factor it out and then solve. So hopefully that makes sense. We're going to start not with this one because this one's a little bit complicated. It's not real complicated, but more complicated than it could be. And we're going to start with a nice easy one and see how this works out. So we want to find dy dx if y squared equals x. So first off, what does y squared equals x look like? Hopefully you guys know. What does that look like?
Sideways parabola.
Exactly. It's just a sideways parabola. Clearly does not pass the vertical line test. Clearly not a function, right? Could be solved for y. If you solve for y, you end up with y equals the square root of x, right? Which is the top half of it. Or you could end up with y equals the negative square root of x, which is the bottom half of it. True?
True.
Okay. So we'd rather not have two different functions to deal with and have to find two different derivatives, because the square root of x and the negative square root of x would give us two different derivatives, right? And then we'd have to know which point we were talking about and which derivative to use, and that'd be a little bit of a pain, especially on some that are going to get far more complicated than this one. So let's see if we can take the derivative with respect to x of both sides of this. And right-hand side should be quite easy, right? What's the right-hand side's derivative?
1.
Oh, why did I write 2y? I meant to write y squared. I don't know why I wrote 2y. There we go. The right-hand side should just be 1. Everybody agree with that?
Yeah.
Okay. So now what we've got going on here is a derivative with respect to x of y squared. Well, that's sort of like when we were trying to use the chain rule on some of these other problems, right? We were looking for the derivative with respect to some variable, but we had to change the variables in it, right? We had different variables in the end than when we started. Is that true? When we were doing the chain rule, right? We converted into u's and maybe v's sometimes and dealt with all these other weird variables. We're going to do the same thing here. We could say that this should be, let's say, u squared with u equal to y. Now, that doesn't sound like it's going to be super helpful to us, but it is. Okay, we're going to call y squared. We'll call this function, what variable you want to use for this. A equals, we'll call it a. Let's say a equals y squared. So this will be a equals u squared with u equal to y. And we are looking for the derivative of a with respect to which variable?
X.
X. So we want dA dx. So dA dx, if we rewrite this as this composition, right, should be dA du times what? Should be times du dy. True?
True.
Okay. So as we do that, what's dA du?
2u.
2u. And what's the derivative of u with respect to y? Well, that's just what?
1.
That's just 1. But as we go through and do this, we have to keep in mind that what we're really doing is we're taking a derivative with respect to x. And so this term here that we're taking the derivative with respect to y has to really be, we really need to do this in terms of x. And so really we have to multiply this by dy dx, because we're really taking the derivative of the y term with respect to x. And so anytime we do this, we're going to end up with a dy dx term at the end. So we got 2u, which is just 2y, dy dx. And anytime we take the derivative of a y term with respect to x, we're just going to end up with a dy dx term attached to it. And you don't actually have to do all of this. All you have to do to make this easier is take the derivative of this with respect to y and then multiply it by the derivative of y with respect to x. Okay? You don't need to write any of this out. So every time you take a derivative of a y term with respect to x, you take the derivative with respect to y and you multiply it by the derivative of y with respect to x. Does that make sense?
Yes.
So dy dx equals 1 over 2y. And that's what you get. That's our derivative. This is our final derivative. And this is clearly very different than any other derivative we've gotten when it was a derivative with respect to x, because it's got a y term in it now, doesn't it? That's okay. If we wanted to know, let's say, what was the equation of the tangent line at the point, what's a good point that's on this equation?
Four, 2.
4, 2. All right, great. How would I find the slope? The slope would be 1 over 2 times 2 would be 1/4. And so it should come out to be y minus 2 equals 1/4 times x minus 4. What if I wanted it to be at the point, let's say, -4? Or sorry, not -4, but 4, -2. Do this up here, the tangent line at 4, -2. Then what should our slope be?
-1/4.
-1/4, and we should get y plus 2 equals -1/4 times x minus 4. And we should see, if we graph these, that this derivative works for any point on here, not just for the top half or for the bottom half, right? Because 4, 2 and 4, -2 are on the two separate halves of it. So if I do y minus 2 equals 1/4 times x minus 4, that gives us the tangent line up here. And if we do y plus 2 equals -1/4 times x minus 4, that ought to give us the tangent line down here at 4, -2. And so it should work for any point on this entire parabola, not just the upper half or the lower half if we'd solved it for, like it would have if we'd solved it for y. Everybody good there or no?
Yeah.
Cool. All right, let's do another one. Y squared equals x minus 1 over x plus 1. So what do we need to do? We need to take the derivative with respect to x of both sides. And what's the derivative with respect to x of y squared going to be? The first thing we do is take the derivative of it with respect to y, which is
Two y.
2y, and then we multiply it by dy dx because we took the derivative of a y term with respect to x. And then over here on the other side, this one we'll get by using what rule?
Quotient.
Quotient rule. So x plus 1, denominator, times derivative of numerator, minus numerator, times derivative of denominator, all over denominator squared. And what does that simplify to? X plus 1 minus x minus 1. And so the x plus 1 minus the x will cancel, and then we have 1 minus -1, so that ought to be a 2 up there in the numerator. So 2 over x plus 1 squared. And if we divide by 2y, the 2's will cancel, right? And we just end up with our derivative is 1 over y times x plus 1 squared. Good or no?
Good.
And we'll notice that for this one, our derivative has both x and y in it, and that's okay. Sometimes these may come out with just one variable, or they may come out with both variables in them, and that's okay either way. Any issues with that? Any questions, problems, complaints? Anything? Everybody good? All right. Let's do another one. What should we do first here? We should take the derivative of
Each side.
both sides with respect to x. So on the left, that's the derivative with respect to x of x. And on the left side, that's the derivative with respect to x of tangent of y. And what's the derivative of x with respect to x?
1.
And what's the derivative of tangent y?
Secant squared y.
Should be secant squared y. Did we take the derivative of a term with a y in it?
Yes.
Yes. So secant squared y dy dx. And so now we'll just divide 1 over secant squared y equals dy dx. Or we could rewrite that as cosine squared y. Good, or now any questions on that? All right. Now we'll get into a more complicated looking one. X squared y plus xy squared equals 6. So what do we need to do?
Do we need to move the y's to the same side, or do we just keep it from there?
No, we can leave it exactly as it is. It doesn't need to be, never need to rearrange these if you don't want to. So we'll just take the derivative of the left with respect to x and the derivative of the right with respect to x, just like we've been doing with the other ones, yeah? Everybody good with that?
Yes.
All right, what's the derivative with respect to x of 6?
0.
0. And then over here, x squared y plus xy squared. Well, first off, x squared y is two functions being multiplied together, isn't it? Two different variables means two different functions. And same with x times y squared. So each of those is going to require us to use the product rule. Okay. So how do we take the derivative of x squared y? Should be x squared times the derivative of the y. And what's the derivative of y with respect to x?
The derivative, you have to, it's 1 times the derivative of y in respect to x.
Right, it's 1 times dy dx, exactly. So I'll just write the dy dx, but if you want to put a 1 there, I guess we could put 1 there, right? 1. Okay. And then we have to add to that the derivative of the x squared, which is what?
2x.
2x. And that one I'm not taking a derivative of a y. So I don't need to put the dy dx, and then it's times the y. And the reason that 2xy doesn't get a dy dx is because nowhere in the second part of that product rule did I take a derivative of y, right? I did the derivative of the y part with the first part of the product rule, and then I just did the derivative of the x part times the y in the second part. Everybody okay with that?
Yes.
All right, and then what about xy squared? So we'll have an x and then a derivative of y squared with respect to x, which should be
0.
What's the derivative of y squared with respect to y?
2y times dy over dx.
Right, 2y dy dx. and then plus, what's the derivative of x? That's 1, and then times y squared. Everybody okay with that or no?
Yes.
All right, cool. Now we've got a bunch of terms on this side that have a dy dx in them, and we got some terms on this side that don't have a dy dx in them. So what we're going to do is we're going to move all the terms that don't have a dy dx in them to the other side of the equation. So I'm still going to be left with an x squared dy dx and a 2xy dy dx, but on the other side, I'm now going to have negative 2xy minus y squared. Everybody good with moving those over? Get rid of those and move them over to the right side. And that leaves me with two different terms that both have a dy dx in them. So I'm going to factor out that dy dx. So if I factor out dy dx from the two terms that were left, that should leave me x squared plus 2xy. Everybody okay with that or no?
Yes.
All right, and then what should dy dx be? It ought to be negative 2xy minus y squared over x squared plus 2xy. Any questions on that derivative, or everybody okay with that? You all surviving this? We're all okay?
Surviving is an adequate description.
All right, well, you only have to survive 11 more minutes of listening to me talk about it. Then you can survive some more of it on your own with homework later. Let's see if we can find the slope of the circle, x squared plus y squared equals 25 at the point 3, negative 4. So first off, what do we need to do? What's the first step we've done each time?
Take the derivative of x of each side with respect to x.
Take the derivative of both sides with respect to x. So the derivative of x squared plus y squared with respect to x should equal the derivative with respect to x of 25. And the derivative with respect to x of 25 is?
0.
0. And what about the derivative of x squared plus y squared? Well, the x squared should just be
2x.
2x, and the y squared ought to be
2y times the derivative of y of x.
2y dy dx. 2y times the derivative of y with respect to x. So 2y dy dx. And now we end up with dy dx equals, well, we can bring the 2x to the other side, right? And divide by the 2y to get dy dx equals negative 2x over 2y, or negative x over y. Everybody good with that being the derivative there?
Yes.
All right, and if we wanted to find the slope at the point 3, negative 4, we just evaluate this at 3, negative 4. So that's negative 3 over negative 4, or 3/4. So the slope should be, so the equation, if we wanted to find the equation of the line, ought to be y minus negative 4, so y plus 4, equals 3/4 times x minus 3. And if we were to go in to Desmos and take a look at this, we'd have x squared plus y squared equals 25. And what do we have? We had y minus y plus 4, right? Equals, what was the slope? Was it 3/4, right?
3/4 times x minus 3.
3/4 times x minus 3, and there it is. There is the line tangent to our circle at the point 3, -4. Right there. Everybody good with that or no?
Yes.
Cool. No issues? Everybody's still surviving? All right. Let's do another nice little easy one of these. These are going to get a lot more difficult eventually, but starting off with ones that aren't too terrible. So 2y equals x squared plus sine y. We want to show that the slope is defined at every point on this graph. So that means that there are no places where this has an undefined, no vertical tangent lines, basically. What are we going to do? We're going to take the derivative with respect to x of both sides. So 2y on the left and the derivative with respect to x of x squared plus sine y on the right. And on the left, the derivative of 2y should become what? What's the derivative of 2y?
2 dy dx.
2 dy dx, exactly. And then the derivative of x squared ought to be
2x.
2x, and the derivative of sine y ought to be
Cosine y times dy dx.
exactly. And so now all we've got to do is get the dy dx terms to one side and solve for dy dx. So how about we subtract the cosine y dy dx? And just leave the 2x on the right by itself. And then what can we do? We can factor out the dy dx over here and then divide by what's left. So what does dy dx end up being totally? It's 2x over what?
Negative cosine y.
Don't forget this 2.
Negative 2 cosine y.
Hold on. If we take out the dy dx, right? What do we have there? We have 2 minus cosine y, right?
Yeah, 2 minus cosine y. Okay.
Yeah, so we got to factor that out. Right? Treat dy dx as if it's just a singular variable there. So we'll divide by the 2 cosine y. And we want to show that the slope is defined at every point. Well, what would make the slope undefined if the denominator equaled
0.
0? So 2 minus cosine y, we want to show that that can't be 0. Well, that would say that the cosine of y can't be 2. And is that true?
Yes.
Why? What do you know about the cosine function? Cosine of anything is always
In between -1 and +1.
in between -1 and +1. So cosine y can never equal 2. And just for fun, let's take a look and see what this function looks like. 2y equals x squared plus sine y. It's like this weird little wavy looking parabola thing. Like a parabola on drugs or something. I don't know. Don't do drugs, kids. Good or no? Some of these have really cool looking graphs, so we'll look at some of them as we go through. Any issues there? Any problems? Any questions, complaints, concerns? Anything? All right, I think, let's see. Yeah. We got 4 minutes. We could probably finish this one. All right, let's do this one. So here we have a figure 8 curve. Y to the 4th equals 9y squared minus 9x squared. We want the equation of the tangent line at the point 2 root 5 over 3 comma 2. So in order to write the equation of a tangent line, we need to find a
derivative.
So the derivative on the left with respect to x ought to be what?
4y to the 3rd times dy dx.
4y to the 3rd dy dx. And on the right, the 9y squared ought to become
18y times dy dx minus 18x.
perfect. And now we just need to solve for dy dx. So I'm going to try and keep this positive. So I'm going to bring the 18x over here and subtract the other 18y dy dx minus 4y cubed dy dx. If you do it the other way, right, you'll have a negative 18 and a 4y cubed minus an 18y. That's fine. Doesn't really matter. And what do we end up with? We end up with dy dx equals 18x over, and when we factor out the dy dx, this is 18y minus 4y cubed. Good or no?
Good.
All right. Those are all divisible by 2, right? So might as well make it a little simpler. 9x over 9y minus 2y cubed. And if we want to find the slope, let's evaluate this at the point 2 root 5 over 3, comma 2. So that's going to give us, let's see here, 9 times 2 root 5 over 3. All over, plug in 2. This is 18 minus what? 16? And that's going to give us the 9 divided by 3. We'll just make this a 6 root 5 in the numerator. And then in the denominator, we've got a 2, which gives us 3 root 5. Everybody good with that or no? Giving us y minus 2 equals 3 root 5 times x minus 2 root 5 over 3. And with any luck, if we go into Desmos and put in y to the 4th equals 9y squared minus 9x squared, we'll get that figure 8 curve. And we should have, what was it, y minus 2 equals, what was our derivative? What was our slope? 3 root 5.
Yeah.
Times x minus, it was 2 root 5 over 3. Is that right? Yeah, looks like it. And there it is, touching it at that point. They approximate 1.491, but it's tangent to the curve right there at that point. Good or no?
Good.
Spectacular.